Hi, today we'll discuss a little bit about operators and some of the things that we need to remember. All right, some of the parts where questions can be asked directly. All right, so we'll discuss the projection operator, the parity operator. All right, these are operators whose properties are interesting, and there can be direct questions from this. Right, unitary operators are quite important in quantum mechanics. And then we'll have a short discussion on commutator algebra. Okay, so most of the relations of commutators are the same as those of the Poisson brackets. So if you are familiar already with Poisson brackets, then we won't have to spend much time for commutator algebra. Right, we can just make comparisons and then move on. We'll also discuss infinitesimal and finite unitary transformations. So let's look at what's called as the projection operator. All right, this is the definition for a projection operator. An operator is said to be projection operator. All right, and there are, if it has to be a projection operator, there are two things that it has to be satisfied. One thing is that it has to be Hermitian, and it has to be equal to its own square. All right, so if in a question an operator is given and they are asking whether it's a projection operator, all right, then these are the two things that you need to check. You need to check whether it is Hermitian, one thing, and you have to check whether squaring the operator gives itself. All right, so this is the definition of the projection operator. All right, now also it can easily be shown that the sum of two projection operators is generally not a projection operator. Right, so these kinds of information are necessary because, see, there are questions for competitive examinations where they ask which among the following are true or which among the following are false, etc. Right, so it's a good thing to remember this. So it's easy to check that if two operators are projection operators, the sum need not be a projection operator. It's easy to check. All right, suppose A is a projection operator and B is another projection operator. All right, this means that A has to be equal to Hermitian and B also has to be equal to Hermitian. Not only that, A square has to be equal to A and B square has to be equal to B. All right, now we can easily check whether A plus B is a projection operator. We can easily check whether A plus B is a projection operator. All right, so A plus B is Hermitian. Obviously, you take the Hermitian conjugate of A plus B, you get A dagger plus B dagger, which is A plus B again. So it's Hermitian. But we need to satisfy another property that when you square the projection operator, you should get itself. So let's check this. This is A square plus B square plus AB plus BA plus AB plus BA. All right, so this is equal to, we have already seen that since A is a projection operator, A square is A. So this is A plus B, and there are these terms AB plus BA. All right, now this part spoils it for A plus B. All right, so A plus B is not a projection operator because A plus B whole square is not equal to A plus B. All right, now what happens if AB and BA are 0? Okay, 0. In this case, this is a projection operator. All right, so there's a special case where this can be a projection operator, but generally, if A and B are projection operators, A plus B is not a projection operator. So, a special case. So, if the product of two operators is 0, we say that the operators are mutually orthogonal. All right, so we can say that the sum of two projection operators is also a projection operator if they are mutually orthogonal. All right, if they are mutually orthogonal. All right, and it can easily be shown that the product of two commuting projection operators is also a projection operator. All right, so we need this extra condition. Let's again think A and B are projection operators. Let's look at AB. Okay, let's look at AB. What's the Hermitian conjugate of it? What's the Hermitian conjugate of it? That is B dagger, A dagger. All right, but A and B are already Hermitian, so B dagger is equal to B, so this is BA. Okay, now this is not really Hermitian unless they commute. Right, if they commute, we can write it as A, B. If they commute, we can interchange them without any cost, and then we can write it as AB. So the Hermitian, so the product of two operators will be Hermitian. Product of two Hermitian operators will be Hermitian if they commute. All right, this is a thing that you can keep in mind. Alright, two projection operators are said to be orthogonal if their products is 0, right? Just as I said here, if their products are 0, then we can say that the projection operators are orthogonal, right? Now, if P1, P2, P3 are all projection operators, then P1 plus P2 plus P3, okay, are all projection operators, sorry, P1 plus P2 plus P3 or any such combination is also a projection operator if they are mutually orthogonal, alright, which means P1, P2, P2, P3 all are equal to 0. Okay, and an important thing I want you to remember is that the eigenvalues of the projection operators can be 0 and 1. Alright, I leave it as an exercise for you to prove this. It's quite an easy thing. It's quite an easy thing to prove it. Okay, alright, but you have to remember this. The eigenvalues of a projection operator are 0 or 1. It can be 0 and 1. Alright. Okay, so you can actually show it from the fact that for a projection operator, p square has to be equal to p. Okay, p square has to be equal to p. So I leave it as an exercise for you to show that if p square is equal to p, then the eigenvalues, the possible eigenvalues can only be 0 and 1. Okay, it's easy to show actually because already you get an idea here. Right, you see that 0 square is 0 and 1 square is 1. Right, so you'll see that the same condition has to be satisfied also by the eigenvalues. All right, so you can try that as an exercise. All right, so whether you try it or not, you remember that eigenvalues are 0 and 1. It can be asked as a direct question. Right, and so let's look at a problem now. Show that the operator, this is ket psi bra psi, all right, is a projection operator, and only when psi is normalized. Right, so they are saying that this operator, this is indeed an operator. Okay, this is indeed an operator, and it is a projection operator if it is normalized. Right, it's easy to see this. Right, first we check for hermiticity. As I said, there are two things that you need to check to see whether an operator is a projection operator. The first thing is hermiticity. Is it a Hermitian operator? All right, so you take the dagger, and I hope you remember the property. All right, if you take this dagger, a ket becomes a bra, etc. Right, so here, so you remember that AB, if it is AB dagger, this is B dagger, A dagger. Am I right? So in the same way, you take the dagger. Sorry, right. So this is, let's say, psi dagger, and then this thing. All right. Let's just now you have to remember that under the Hermitian conjugate, when you take a Hermitian conjugate, a ket becomes a bra and vice versa, right? So that this means that okay, this means that this thing, the first part, okay, the first part here, it becomes the corresponding bra. Alright, so that's already a bra, so it becomes the corresponding ket, and the second one becomes a corresponding bra. Okay, so that indeed is what we started with. So it is Hermitian. Right? Now the second thing you need to check whether the square is equal to itself. Is the square equal to itself? So you take the square here. Okay, square means you just multiply these things, right? And immediately we see the advantage of using the Dirac notation, right? So multiplication is just combining these things. Multiplication is just combining these things. So we just write them together, right? And writing this together means you have got a term here, the inner product of psi with itself, the inner product of psi with itself, right? So this indeed is a number, it's an inner product, so we can pull it outside. Let's write it as psi, and then what is left is this thing, right? What we need is this part only, because the square of this has to be equal to the same thing. Am I right? That means that the inner product has to be equal to 1. Right? So this thing is a projection operator if and only when the psi is normalized. Right? Now this is one fact that we use often. Right? We'll take an orthonormal basis. Let's say phi I. All right, and then this thing phi I, okay, no summation implied, phi I is indeed a projection operator. All right, this is an orthonormal basis set, and this is a projection operator. What happens if you act it on some state psi? Right, so you get a component here, This would be a number, a complex number generally. Let's call it as Ci. So this becomes Ci phi I. You get another vector in the direction phi I. Alright, you get a vector in the direction phi I. Right? Phi I is something like a unit vector. We have talked about the basis. Alright, so this is an important kind of projection operator that we use in quantum mechanics. Alright, what do we mean by an inverse of an operator? The inverse of an operator we write as A inverse. It means that if you take the product with A inverse with A and A with A inverse equal to I, right? I is the what do you call as the unit operator, the unit operator. Alright, so this is the state. This is the operator that leaves any state unchanged. It leaves any state unchanged. Okay, that's called as the unit operator. That's the inverse operator. Now we have got a unitary. We have got an important class of operators called unitary operators. All right, the unitary operators are defined like this. If an operator U is called a unitary operator if U dagger is equal to U inverse. All right, if U dagger is equal to U inverse, this means that U dagger is equal to U dagger U has to be equal to the unit operator. All right, this is the definition for a unitary operator. Now this is an important property. You can check this out. Right? You could also do it as a problem. The product of two unitary operators is also unitary. Right? The product of two unitary operators is also unitary. Right? So imagine U and V are unitary operators. All right? Which means that U dagger equal to U inverse and V dagger is equal to V inverse. Okay. Now we check for UV. So you do UV dagger. Alright, you do UV multiplied by UV dagger just to check if it's a unitary operator. Alright, and what's UV dagger? It's actually V dagger U dagger. Right, that's what we have written here. It's V dagger U dagger. And since V is already a unitary operator, V dagger is I and U dagger is also I. So you get it back. Alright, so it's a thing that you need to remember, that the product of two unitary operators is also a unitary operator. Okay. Now this is true actually for any number of operators. All right, if you have an n number of unitary operators, the product of all these unitary operators will also be a unitary operator. Okay, so you can check that here. All right, here is a simple problem. What conditions must the parameter epsilon and the operator g, okay, we have got an operator here, okay, should satisfy so that the operator U is equal to e raised to I epsilon g, right? E raised to I epsilon g, right? Yeah. So we have constructed an operator here. It's U equal to e raised to I epsilon g, right? So we need to check what are the conditions that epsilon and g must satisfy so that this is unitary, right? So it's easy to check. You take the dagger of this e raised to I epsilon g dagger. Okay, so we demand that this is equal to, all right, this is equal to e raised to minus I epsilon star g dagger. Am I right? This is e raised to minus I epsilon star g dagger. All right. Now, if this has to be unitary, this must be equal to e raised to minus I epsilon g. Okay. Because e raised to I epsilon g and e raised to minus I epsilon g are inverse of each other. They are inverse of each other. All right. So what we do to check this is we start with this operator given. Okay. We take the dagger. And you remember the rule. All right. If you have a function, you have to complex conjugate it. So this becomes e raised to, since there's an I here, that becomes a minus I. And epsilon will become epsilon star and g will become g dagger. Okay. Now, if this has to be unitary, this u dagger has to be equal to u inverse. This means that this must be equal to e raised to minus I epsilon g, because clearly this is the inverse of this thing. All right, e raised to minus I epsilon g is the inverse. So the condition is satisfied if epsilon star is equal to epsilon and g dagger is equal to g. Right, and g dagger is equal to g. So the condition is that epsilon has to be equal to epsilon star and g dagger has to be equal to g. This means that epsilon has to be a real parameter and g has to be a Hermitian operator. Right, epsilon has to be a real parameter and g has to be a Hermitian operator. Right? Now, if you don't have an I here, All right, you can think of some operator e raised to epsilon, let's say, okay, O cap, some operator. All right, now you can show that this is actually unitary if O is anti-Hermitian. All right, it can be asked like this. It has been asked in some competitive exam. All right, so what's the condition for e raised to epsilon O to be a unitary operator? All right, if epsilon is a real parameter, and then we see that O has to be equal to minus O dagger, which means it has to be skew Hermitian. All right, so if there's an I here, then this has to be a Hermitian operator, and if it's not, if there's no I here, then this has to be an anti-Hermitian operator. Right? Now we know that Hermitian operators have a special place in quantum mechanics, because we know that all observables, all right, or measurable quantities are represented by Hermitian operators, not any operators but Hermitian operators. All right, so that's the reason why we write unitary operators. Since we are familiar, it's useful to work with Hermitian operators. We normally write this I outside so as to make this operator a Hermitian operator. All right, so this is the form in which we'll often find a unitary operators. Right, it will be of the form e raised to I, some real parameter, and a Hermitian operator. Okay, these are the kinds of unitary operators that we will come across very often. Right, okay. Now we go to the parity operator. All right, so a parity operation is actually a space reflection about the origin. All right, so you make x to minus x, y to minus y, and z to minus z. All right, that's known as a parity operation. Okay, so this is inversion or parity operation. All right, this is called a discrete transformation. Now we define the parity operator in this way based on its action on the, let's say, the position vector. All right, or the position, let's say the eigenstate, the position eigenstate. All right, the parity operator acting on R, or the position eigenvector, position eigenstate, will invert it. All right, it will give you minus R vector. Okay, and it's true also in the opposite direction. Right, so in this way we say that parity operator acting on a function behaves like this. It changes R vector to minus R vector. It changes R vector to minus R vector, and P vector to minus P vector. All right, so this is what happens under a parity operation or an inversion. All right, R vector will go to minus R vector, and P vector will go to minus P vector. In fact, all vectors will behave like this under a parity transformation. All right, all the vectors will go into a minus of itself under this kind of a parity transformation. This is a property of vectors. All right, now there are some other vectors which don't behave like this. For example, if you look at the angular momentum operator, which is also called as a vector operator. This is R vector cross P vector. Right? What happens under a parity transformation? R goes to minus R and P goes to minus P. So L goes to simply R cross P itself. Right? So L goes to L itself, not to minus L. Right? Actually, such vectors are called pseudo vectors. You might remember this. Such vectors are actually called pseudo vectors. Even though we call them vectors, they are actually pseudo vectors. All right, they don't behave entirely like vectors. All right, they have a small problem there. They are actually, for that reason, they are called pseudo vectors. Okay, all right. And again, some of the properties: the parity operator is Hermitian, and the square of the parity operator is the unit operator. Right, the square of the parity operator is the unit operator. Right, so if you remember the projection operator, the square of projection operator is itself, whereas the square of the parity operator is the unit operator. Okay. In other words, it's its own inverse. Right, the parity operator is its own inverse. Right, now it can also be seen that clearly parity operator is also unitary. Right, see, for example, parity operator with dagger. Right, is this equal to the unit operator? That's the question we ask to check if it's a unitary operator. All right, so this becomes pi, because why? Pi dagger is equal to pi. Pi dagger is equal to pi. This is equal to pi square, which is by definition for a parity operator, when you take the square, you get the unit operator. Alright, so you see that pi dagger is equal to I, which means that it is also unitary, right? So this is one operator which is both Hermitian and unitary, right? The other unitary operators that we defined, okay, formed using e raised to I epsilon g cap, right? These are not Hermitian themselves. These are themselves not Hermitian, but they are unitary, all right? G is Hermitian, but e raised to I epsilon g is not Hermitian, all right? But this is one operator which is both unitary and Hermitian. And also the eigenfunctions of the parity operators. We can talk about the eigenfunctions of the parity operators. There are two eigenvalues which are plus or minus 1, right? Since the square of the operator is 1, the eigenvalue also has to satisfy the same condition, and you see that there are two possibilities. It is plus or minus 1. Okay. Now 1, if it is plus 1, we call it as an even eigenfunction, and if it's a minus 1, we call it an odd eigenfunction. All right. Okay. Now in non-relativistic quantum mechanics, the parity operator commutes with the Hamiltonian operator. Right. It's another way of saying that the Hamiltonian has the symmetry, does not change when you invert the coordinate system. Okay. Or parity is conserved in non-relativistic quantum mechanics. When you go into quantum field theory, things are a bit different in particle physics, etc. But in our thing, we'll always have the parity operator commuting with the Hamiltonian. Okay, parity operator commutes with the Hamiltonian, which means that the laws of quantum mechanics, right, behaves the same way even when you view it in a mirror. Right? If there is some quantum mechanical process and you are viewing it in a mirror, you are viewing a mirror reflection of it, you wouldn't see a difference. You wouldn't feel any difference. All right, that's a basic symmetry of non-relativistic quantum mechanics, so to speak. All right. In particle physics, of course, there's this thing called parity violation, and things get quite interesting there. All right. And there's one detail that I want to give you. So the eigenfunctions of the parity operators are even and odd functions. Even and odd functions. Okay, even and odd functions. Right? Even functions are which do not change under a parity operation. Right? Odd functions are which change under a parity operation and goes to minus of itself. All right? For example, let's take the most famous example. Sine x is an odd function. All right, it goes to minus sine x when you take x to minus x. Right? But cos x is an even function. It goes to cos x itself when you substitute minus x in the place of x. All right, so sine x is an odd function and cos x is an even function. Right? So these are typical eigenfunctions of the parity operator. Right? These are typical eigenfunctions of the parity operator. This is an even parity eigenfunction and this is an odd parity eigenfunction. And there is something quite interesting here, because we have seen that parity operator is actually Hermitian. Right? So the eigen vectors of a Hermitian operator form a complete set. We can use it as a basis to expand any function. Am I right? We have seen these things. Right? And this is actually what you see in what you call as the Fourier series. This is actually what you see in a Fourier series, which you might have studied in the mathematical physics. Okay, so you see that you are actually learning something called the Fourier series from here. What you do in Fourier series is actually, right, let's not worry about the details. What you do there is actually expand any function in terms of sine x and cos x. All right, so sine x and cos x, they form a complete set. Right? It forms a basis. You can expand any function in terms of this set of basis vectors, all right, or the eigenvectors of the parity operator. Now to the commutator algebra. Okay, so let's just go through this. The commutator is defined as AB minus BA. Okay? We also might come across what's called as an anti-commutator. It's given as AB plus BA. Okay. So you might come across anti-commutator in statistical mechanics, in quantum statistical mechanics, etc. Okay. Now we say that two operators commute if their commutator is 0. Right? If A with B commutator is equal to 0, then we say that they commute. Right? And it's also clear that any operator will commute with itself. Right? A with A is equal to 0. Now so notice that if two operators are Hermitian and their product is also Hermitian, okay, then these operators commute. Right? So A B whole dagger is B dagger A dagger, which is equal to B A. Okay. Now if AB is also, right, if AB is also a Hermitian, right, and their product is also Hermitian, right, so you need the product also to be Hermitian. So if AB dagger is equal to AB, we have AB is equal to BA, right, we have got AB is equal to BA. So it's clear that if two operators are Hermitian, right, if A and B are Hermitian, right, and plus their product is also Hermitian, then these operators must commute, right. This is kind of obvious, but it can be asked, right. This means that you have got two operators which are Hermitian, right. AB, this is Hermitian, it's given, right, which means that A dagger is equal to A and B dagger is equal to B. This is given. Alright. Now what about AB dagger? In addition, if AB dagger is equal to AB, in addition, if AB dagger is equal to AB, then we can say that they commute. Alright, they commute. That means A and B will commute. Right, AB dagger is equal to AB. This means that, okay, we can just show that here. B dagger, A dagger is equal to AB, but already we had said that A and B are what is a Hermitian, so BA is equal to AB, or AB minus BA is equal to 0, or A comma B is equal to 0. Alright, so this is one question, a slightly roundabout question that can be asked. Alright, if two operators are Hermitian and their product is also Hermitian, then these operators will commute. Right, this is a potential question that can be asked from which among the following is true, which among the following is true. Okay, you could as well do it as a problem, as an exercise. Show that two operators commute if they are Hermitian and their product is also Hermitian. Right. Now let's look at some properties. The first thing is antisymmetry, which is exactly the same thing that we had seen in Poisson brackets. All right, if you interchange the arguments in the commutator bracket, you get a minus sign. Okay, this is exactly the same property that we had in Poisson brackets. All right, there's also linearity. Again, we had seen this in the Poisson brackets. Okay, we have got the Hermitian conjugate of a commutator. It's A B dagger is equal to B dagger A dagger. In this sense, it acts just like a product. Right? We know that A B dagger is equal to B dagger A dagger if they are product. Right? If it's a commutator also, this is true. That's all. Right? If it's a commutator also, this is true. Right? You can easily show that this basic property actually translates to this. All right? You can. I leave this as an exercise for you. Use the basic definition of the commutator and prove this. Prove it. Okay. There's also distributivity. This is also exactly the same thing that we had seen in Poisson brackets, but here we have to be careful about the ordering of the operators. All right, we have to be careful about the ordering of the operators. In Poisson brackets, we are not worried about ordering. All right, because you didn't worry whether x comes first and p comes second, doesn't matter in a multiplication. All right, but in quantum mechanics it matters, so we have to be a bit more careful when dealing with commutators. All right, so A with BC, how do you do that? How do you do that? You check like this. All right, first you take A with B. Okay, first you take A with B, and there is this C left out. Okay, where should you put this C? Okay, so you see that this C comes after B in this thing. All right, so you preserve that order and put the C here. Right, if you put a C here, like we were careless using Poisson brackets, then you would be wrong. All right, so then since this C comes after this B here, you put this C outside here. Right, and there is one more combination that you need to take. It's A with C. Okay, A with C. Right, and you see that in this combination B comes before C. Right, so you cannot write B here. We cannot write B here. You have to preserve the order and write B right here. Okay. All right. Now you can do as an exercise. You can check this thing. I think we had done for Poisson brackets. What is A B with C D? All right. You can actually use the same rule. All right. You can distribute this thing. You can take all the combination A with C, A with D, B with C, and B with D. You can take all these commutators and just be careful to put the A and C, whatever operator comes outside of the Poisson bracket. You be careful to preserve the order, right? And then you'll get the correct answer. You can check this. This is an exercise for you. Find And be careful with this. Find A, B with C, D. All right. Now, you don't have to remember it, but if you remember it, maybe you will be able to solve one or two problems really quickly. And of course, it also obeys the Jacobi identity, just like the Poisson brackets. All right. I want you to prove this as an exercise. All right. This is a problem I leave to you. You prove this thing. Right? You can just use the fundamental definition of a commutator and prove that it also satisfies a Jacobi identity. Right. So it's really clear that the Poisson brackets and commutators have similar structure. They have exactly the same structure. They are known as a Lie algebra, but we won't go into the details. Okay. All right. So there is a connection. There is a formal connection, at least, between quantum mechanics and classical mechanics. All right. Wherever you can write the equations of classical mechanics in a Poisson bracket formulation, and then there is a way to go from there to the corresponding quantum mechanical equations. All right. It's known as a canonical quantization. Right. So the commutator with any scalar is 0. That's another property. Okay. And I want you to remember the fundamental commutators. Ri with Pj is IH cross delta Ij. All right. This is the commutator. These are operators. All right. So this means that x with Px is 1. Similarly, y with Py is 1. So not 1, it's IH cross. I'm sorry. X with Px is IH cross, y with Py is IH cross, z with Pz is IH cross. All other combinations are 0. Okay, all other combinations are 0. X with Py is 0, etc. Okay. Now you see that if you didn't have these operators here, and these were the Poisson brackets, then you would have 1 here. Right? So you see that the formal correspondence can be written like this. You take the equations of classical mechanics in the Poisson bracket formulation. Right? Now I will denote the Poisson brackets like this. Right? And you substitute them by the corresponding commutator. Okay, corresponding commutator. Not only that, if you have some functions a and b here, you should change them to operators. All right, you should change them to operators, and then you will get the same. You will get all the quantum mechanical commutator results. All right. So here, for example, we know that x with px Poisson bracket. Let me just write it here for better visibility. Okay. So all right. So here, if x with px, the Poisson bracket, we know that it's equal to 1. Right? So to go to the corresponding quantum mechanical thing, what you do is that you substitute or you change this Poisson bracket to the corresponding commutators with a 1 by IH cross, and these things appearing inside, you write them as operators and put equal to 1. Right? Then you get the fundamental Poisson commutator bracket. Okay, x with px equal to IH cross. You just cross multiply. All right. So this is something that makes things rather easy. Right? I want you to remember this, and this is a fundamental commutator. You have to remember this. All right. In fact, we can obtain quantum mechanics just by postulating this thing. All right. We can, you can go to quantum mechanics axiomatically. All right. We can make an axiomatic formulation for quantum mechanics. We can actually just start using this fundamental commutator relation and then demand all the properties of commutator, and you can find solutions to this equation, and you'll see that if these are in the coordinate representation, you'll get the corresponding x and IH cross d by dx, etc. Right? So you can, just like the Poisson brackets, the fundamental Poisson brackets, and all the properties can be used to formulate classical mechanics in an axiomatic way, you can use the commutators and the fundamental commutation relation to formulate quantum mechanics in an axiomatic manner. Okay? You can just postulate these things and derive quantum mechanics out of it. All right. So let's do a couple of example problems. Show that the commutator of two Hermitian operators is anti-Hermitian. Okay, so I think I leave that as exercise for you. It's completely solved here. I don't have to go into the details. All right, you can easily check. All right. Now the second question is evaluate the commutator A, then B, C, D. Okay, so what we have here is you can consider it as a product of operators. You can consider them as a product of operators. So you can use the distributive property. Use the distributive rule. Distributive rule. and then you expand and find the final answer. Okay, this is a question that was asked in one of the previous examinations. All right, the answer is this. We can check this. Use the distributive property and then just do it. All right, so I leave it to you. It's not particularly complicated. You just use the distributive rule. Okay, maybe I'll do the first step here. This you write it as A with BC multiplied by D, okay, plus commutator of BC multiplied by commutator A with D. Right, that's it. Now you expand it using the fundamental definition and you'll get to this answer. Okay. All right. Yeah, all right. Now we go to unitary transformations. All right, so I'm giving in one class all the definitions, all the things that you need to remember, so that you can look at these notes and just revise before the examinations. All right, these are things that you need to keep in your mind. Okay, so this is unitary transformation. All right, we know that an operator generally changes a vector to another vector. All right, so if you act a unitary operator, also it changes to another vector, and such a transformation we call as a unitary transformation. All right, so psi prime is equal to u psi. This is a unitary transformation. Right, and obviously you can take the dagger or ket on both sides, and you see that psi prime is equal to bra psi. Sorry, bra psi prime is equal to bra psi multiplied by u dagger. Just dagger on both sides. All right, and you'll get this result. And it's important to remember that a prime is u dagger. Right, so the state changes when the state changes are psi to psi prime. This is equal to u psi. Okay, if this is the transformation that we are talking about, then the corresponding transformation will take the operator. All right, a goes to a prime, and that's equal to u dagger. Right, again I leave it as an exercise for you to prove this. Just prove it. All right, you can do it as an exercise. You can check the textbook if you don't know how to do that. You can check any textbook or try to do it by yourself. All right, try to do it by yourself. Now, but you have to remember this. All right, a prime is equal to u dagger if psi prime is equal to u psi. All right, and you can also consider the opposite case, because u dagger is also a unitary operator. Right, it's just a matter of convention which one you call an operator and which one you call the inverse operator. Right, so you can say exactly the same thing here. If psi, if you look at the inverse transformation, all right, psi is equal to u dagger psi prime. You take psi prime and you make an inverse unitary transformation, you will get psi, obviously. All right, because you got psi prime by doing a transformation on psi, a unitary transformation on psi. So you take a unitary transformation on psi prime, or you can just multiply by u dagger on both sides and see. Right, you take the inverse transformation and you get psi back. All right, and the corresponding transformation is a is equal to u dagger a prime u. Okay. A is equal to u dagger a prime u. Okay. What's the importance of unitary transformations? It is that the inner product is preserved. The inner product is preserved. You show this, all right? Show this thing. You show that inner product, right? You show that psi prime psi prime is equal to psi. Right, psi prime is equal to psi. This is what you mean by this is what you mean when you say that the inner product is preserved. Right, you make a unitary transformation to vectors, the inner product remains the same. This means that the physics remains the same, because we know that all the physics are based on the inner products. We define the probability, etc. You see that the probabilities do not change. Right, we are talking about probabilities in quantum mechanics, and these probabilities does not change if you make a consistent unitary transformation. All right, the probabilities, the inner products do not change. Okay, so you can say that unitary transformation, that's why unitary transformations are important. Unitary transformation does not change the physics of a system. It does not change the physics of a system. Okay, it merely transforms one description of the system to another physically equivalent description. All right, in particular, as an example, you can actually work on quantum mechanics from any basis. Right, you can take the what do you say, the eigenvectors of any Hermitian operators as the basis. So you can choose to describe the equations in any basis that you choose, right? And these are all equivalent because all these basis transformations, all right, they are related by a unitary transformation, all right? So when you go from one set of basis or one basis set to another basis set, we see that they are related by a unitary transformation, all right? So you remember that unitary transformations relate one orthonormal basis to another, okay? So it doesn't matter in which basis you do. Maybe some basis we are more convenient, for example, the position basis in which we write the Schrodinger equation, etc. But it's not unique, all right? You could use any basis and you get a physically equivalent description, all right? That's not the only thing. We need these unitary transformations when we talk about symmetries of a system, okay? We can say that the system is invariant under rotations, right? The physics does not change under rotations. So obviously this rotation can be given by a unitary transformation. We can actually show that the rotation is a unitary transformation. Similarly, time translation, all the symmetries, all right, all the symmetries of the system, we'll write it as unitary transformations, all right? So unitary transformations are of fundamental importance in quantum mechanics, all right? Even time translation, all right? Time translation, we know that energy conservation and time translation are related and all that from Noether theorem. We'll be discussing that in more detail in quantum mechanics also, okay? But these connections are there, right? Unitary transformations are of fundamental importance in quantum mechanics. It's very important actually. It's very important that time evolution is a unitary transformation, right? Time evolution is actually a unitary transformation. It's called a unitary evolution, okay? Unitarity of time evolution, it's actually a fundamental property of quantum mechanics. It's also known as a conservation of information in other words, all right? The fact that the time translation is governed by unitary transformation, so time translation is a unitary transformation. It's also known as conservation of information, or it's associated with what we call as conservation of information. But that's not important. We'll just leave it at that. Now we can talk about infinitesimal unitary transformations, all right? So you can talk about an infinitesimal unitary transformation. What's an infinitesimal unitary transformation? An infinitesimal transformation is a transformation that differs only infinitesimally. Here epsilon is an infinitesimal parameter, right? It differs only infinitesimally from the unitary operator, right? Which means that if you make a unitary transformation, you are doing nothing, right? It means that you are keeping the system as such, right? And to that transformation, you are making an infinitesimal change, all right? That's why we call it as an infinitesimal unitary transformation. So an infinitesimal unitary transformation is a transformation which differs only infinitesimally from the unit operator, all right? From the unit operator. Okay. Here epsilon is a small parameter, an infinitesimal small real parameter, and G is a Hermitian operator, all right? You can actually show that this I leave as an exercise to you again. Show that U dagger U is equal to I. All right. So here the trick is that since we are talking about infinitesimal things, you have to neglect terms of order epsilon square and greater. Okay. You can take the product of U dagger and U. Of course, U dagger is I minus I epsilon G. Okay, G is Hermitian. All right. So when you take the product, you can neglect the terms which are higher order in epsilon. All right. Only then you will see that U dagger U is equal to U dagger equal to I. But you can prove this. Okay. I leave it as an exercise to you. You can do it right now. All right. Now, what happens to a state vector under infinitesimal unitary transformation? All right. We can say psi goes to psi plus delta psi. It changes infinitesimally. All right. Psi goes to psi plus delta psi. And what is this delta psi? It's I epsilon G acting on psi. All right. So this is, you will come across such kind of things. Okay. These are important rules. All right. And what happens to an operator when you make the transformation? We saw that it's U dagger. Okay. So you just make this multiplication, neglect the higher order terms, and you see that the first order variation, all right, the first order variation is proportional to the commutator between G and A. This is a nice result, all right. You see that the first order change of an operator under unitary transformation is proportional to the commutator. Okay, commutator of that operator with the generator of the unitary transformation. All right, here G is usually called as the generator of this unitary transformation. This is called the generator of this particular infinitesimal unitary transformation. All right, and you see that the operator, okay, this has important consequences. All right, we'll look at that later on. All right, I'll repeat, when an operator, like if you make a unitary transformation to an operator, you have got a generator for this unitary transformation. All right, the change in that operator, the first order change, all right, the change in that operator is proportional to, okay, the commutator of that operator with the generator of the transformation. All right, we'll see that this is important when we look into symmetries. All right, now once we have infinitesimal unit transformations, we can construct finite. If we have infinitesimal unitary transformations, we can construct finite unitary transformations from them. All right, you just do a large number of infinite number of infinitesimal transformation, and then you get a finite unitary transformation. All right, that's exactly what we do here. We make this infinitesimal unitary transformations a large number of times. All right, and then you'll get what you call as, so this small infinitesimal transformations will build up into a finite unitary transformation. It's just like talking about rotations. All right, you can talk about a finite rotation, you can build up a finite rotation from infinitesimal rotations. All right, here alpha by n is the infinitesimal parameter. All right, so this is epsilon here, this is epsilon. Okay, so alpha here is a finite parameter, and we have divided into a large number of pieces, each of what is a magnitude epsilon, all right, or value epsilon. Okay, and you just take this product, and then you'll see that it actually boils down to e raised to I epsilon g cap. Okay, so what do you say, this infinitesimal transformation, if you do it a large number of times, you will see that it builds up to a finite unitary transformation. Okay, finite unitary transformation. All right, if you remember, this is exactly the kind of unitary operator that we talked about in our one of our previous problems. Okay, so you will see later on that the rotation or time evolution, finite rotation, finite time evolution, or finite space translation, all these things will be written as a unitary operators of this form. Okay, all right, you can actually try to play around a little bit with this. Okay, I can also ask to prove, I just ask you to look into this and convince yourself that this indeed is the case. All right. All right, and generators of unitary transformation. We said that if you have a Hermitian operator, all right, if you have some Hermitian operator G, then immediately you can think about a unitary transformation. Right? Immediately you can think of a unitary transformation. This means that any Hermitian operator is a generator of some unitary transformation. Okay, every Hermitian operator is a generator of some unitary transformation. Right? And without showing this, actually, you might already have guessed that, just like in classical mechanics, the Hamiltonian operator is a generator of time translation. Okay, the unitary operator called time translation. Momentum operator is the generator for space translation, and angular momentum operator is the generator for rotations, etc. Right? So corresponding to every unitary transformation, you can think about a Hermitian operator. All right, just to conclude, we'll be using all these properties later on when we go into some of the problems, including, let's say, we'll be talking about angular momentum algebra, and where we'll deal with some sorts of things like this, commutators, the properties of commutators, and all these things. Okay, and another aspect that we might need for exams, all right, some information you need for examinations are based on the trace of an operator. All right, so trace is something that's invariant when you change basis. Okay, it does not change when you change the basis. All right, so this is an important quantity. You remembering this may be helpful. Right, just keep these things in your mind. Right, I just wanted to be complete, so you have these things, you can revise them before the examination. So trace of A what do you mean by trace of an operator? Right? To find the trace of an operator, what you do is that you expand that operator in a particular basis. Right? You know that an operator can be represented as a matrix, and then you take the trace of that matrix. Right? So in order to represent an operator by a matrix, you have to go to a particular basis. Okay, you can go to a particular, for example, if you have basis set phi I, let's say if you have basis set phi I, all right, then any matrix, any operator can be represented as matrix elements Aij, all right, where Aij are the matrix element phi I, A, phi j, right? You might have already been familiar with this. This is known as the matrix elements of A between the basis vectors phi I and phi j, all right? This is Aij. This is known as the matrix element, okay, of operator A between the eigenfunctions phi I and phi j, etc. Okay, I hope you have seen these things. And if this phi I and phi j are eigenfunctions of this operator itself, then you will see that this will be a diagonal matrix. Okay, you'll see that it will be a diagonal matrix, and then the trace is actually the sum of eigenvalues. You can say this trace is actually sum of eigenvalues. Okay, it can be easily seen. This is what you mean when you talk about a matrix representation of an operator. All right, you take this combination of that operator, and then you get a matrix. All right, but it doesn't matter which basis you use. The trace is invariant. All right, trace is independent of the basis used. All right. Another important property is that you can make a cyclic permutation. You can make a cyclic permutation of the arguments. Okay, you can take the product of many operators and then find the trace, and you'll see that this property is satisfied. All right. Even if you put this d to here, okay, you get the same trace, and then you can do the same thing. You can bring this c here, and again the trace will be same, etc. Right. So if you make a cyclic permutation of these operator products, okay, the trace does not change. Okay, so it's easily seen that for this reason trace of AB is equal to trace of BA, and I want you to remember that trace of A plus B is trace of A plus trace of B. Okay, now just to conclude, let's look at some other useful theorems. Okay, we'll talk about these things. The eigenvalues of a Hermitian operator or a Hermitian matrix are real. Okay, and eigenvectors from an orthonormal basis. We have already seen this. I just want to repeat this, right? And the eigenvalues of a skew Hermitian matrix or an anti-Hermitian matrix are purely imaginary or zero. They are purely imaginary or zero, right? There's also the eigenvalues of a unitary matrix. These are unimodular. Unimodular means the modulus has to be equal to 1. All right, these are complex numbers whose modulus is equal to 1. All right, so there can be a question where they ask, right, which among the following can be an eigenvalue, okay, of a unitary operator, and you just check whether these are unimodular, if their modulus is equal to 1. Right? How do you find the modulus? You just find so if you have a complex number a plus ib, all right, what's the modulus of it? It's square root of a square plus b square. All right, that's known as the modulus. Okay, so this z, then z star is equal to a minus ib. So you just have to find z star. All right, you just have to find z star, and you can check whether it is if the modulus is equal to 1. Okay. All right, with that we'll conclude this session, and immediately we'll go on to the next session. We'll start with the Schrödinger equation and some of the problems. All right, we'll start with the one-dimensional problems including the infinite square wave potential particle in a box, what's it called, the harmonic oscillator, an important problem. Right. Next thing we are going to discuss are this, and in between we have one more thing to discuss. There are pictures of time evolution. There's the Heisenberg picture and the Schrödinger picture. Okay, maybe we'll discuss that first. Okay, and in relation with that, we'll also discuss the connection between symmetry and conservations. All right, so these are things that you have to mainly remember. All right, and we'll be using maybe these insights to solve problems later on. But other than that, these are some of the things you have to keep in mind. Okay, so I'll see you in the next session. Thank you.